Hello, my dear friends. Today I will discuss with you a very important phenomena, which is length contraction. Length contraction can be derived in a number of ways. Okay. Perhaps the simplest is based on the time dilation and using the principle of relativity. Let I take an example. Let us consider what happened to unstable particle which is called the muons. You know the muons, the fundamental particle. And it is created at the high altitude, okay, at the high altitude from the Earth's surface. And it is created by the fast cosmic ray particles like protons when they enter the Earth atmosphere. Okay, the cosmic ray particles, they are from the space, and when they enter the Earth atmosphere, then they collide. Then they collide with the atomic nuclei. Then they collide with the atomic nuclei in the Earth atmosphere. Then the muon is created. And the muon has a mass 207 times that of the electron and having the charge plus E and minus E. But muon is unstable. It decays into an electron or a positron. After an average lifetime of, what is the average lifetime of the muon? Is unstable, very small, 2.2 microseconds. Micro is 10 raised to power minus 6 seconds. So now you think of it, the muon, it enters the Earth atmosphere and having a very small lifetime, 2.2 microsecond. How much distance it could travel then in the Earth atmosphere? Now you will say, like you are having a question, what's the velocity of the muon? Muon velocity is very high. You know how much? 2.994 into 10 raised to power 8 meter per second. Very near to the velocity of light. How much? 0.998 c. What is c? The velocity of light. And it is having very high speed, but having a very small lifetime, and it reaches the sea level, in a good quantity, the large number of muons they reach. Okay. Now the problem is, first of all, we try to find how much distance it could travel before they decay. Okay, and that distance, how you calculate that? We can calculate that distance, velocity into the lifetime. What is velocity? 2.994 into 10 raised to power 8. And what is the lifetime? 2.2 into 10 to the power minus 6 seconds, multiplying the two. And the distance becomes simply 0.66 kilometer. Then a question comes in your mind, if they could travel only 0.66 kilometer and they are created just when they enter the Earth atmosphere, then how they reach the Earth's surface? Because the Earth atmosphere is more than 10 kilometer. This is a problem. And they are created almost at an altitude of around 6 kilometers or more. So to resolve the paradox, we note that the muon lifetime is okay, 2.2 microsecond, and it is for that observer which is traveling with the muon, which is traveling in that frame where the muon is. But when we will observe the lifetime of the muon, it will not be 2.2 microsecond, it will be delayed, because we know the time dilation. Time dilation means if we are in a different frame other than the muon frame, then definitely, because muon is traveling with very high speed and we are in a different frame, and for us the time will be longer, the decay time becomes longer. And how we'll calculate that? By using formula t is equals to t naught under root of 1 minus v square over c square, and t naught is the exact time, proper time as observed by muon itself. Using this relation, the time which we will observe, it is not 2.2 microsecond because it is delayed and it is now 34.8 microseconds. For us, the decay time is 34.8 microseconds. And in, for a moving muon, having the lifetime almost 16 times longer, 34.8 microsecond means 16 times longer than 2.2 microseconds. Then for us, how much distance they can travel, the muon can travel. Now applying the same formula, velocity into time, velocity is 2.994 into 10 to the power 8, and time is 34.8 microsecond, 34.8 into 10 to the power minus 6, and how it comes out 10.4 kilometer. So okay, the problem is solved. For us, the muon traveled a distance 10.4 kilometer, right? Now let's think over the situation, how the muon observes how much distance now it travel, it crosses. Because if we are in a muon frame, then lifetime is 2.2 microsecond, no problem. Okay, then how much distance the muon feels that a person which is in the muon frame, what is the distance traversed? Now the Earth atmosphere for a person which is in the muon frame, that atmosphere is not like 10 kilometer in size. It contracted. And how we find that, how much it is? Let I use a formula that L equals to 10.4 under root of 1 minus v square over c square. When I am using this formula, L equals to L naught and this all, and would the distance becomes, how much it becomes? Only 0.66 kilometer, because we are in the muon frame, and for us the atmosphere height, atmosphere thickness will not be like 10.4 kilometer. It would be only 0.66 kilometer. It is contracted. That is called the contraction, length contraction. In a muon frame, the atmosphere length is contracted. So okay, the problem is solved. Therefore muon like 2.2 microsecond, and the atmosphere is contracted, and it is only 0.66 kilometer, so it travels that distance. And for us, the lifetime is 34.6 microseconds, and then for this time it covers a distance 10.4. So we are starting now length contraction, relativity of the length, that is the length contraction. We are having considered the two inertial frames, S dash and S. S dash is moving at a constant velocity. This is S dash. It is moving with constant velocity v, and there is a rod. There's a rod, there's a rod AB in the moving frame. It is placed along the axis. This is O point. It is placed along the axis OX dash, right? It is placed along the axis O dash X dash, O prime X prime. And if there is observer in the frame S dash, for the observer in the frame S dash, the length of the rod will be, what is the length of the rod for the observer which is in the frame S dash? That length will be simply OP, O dash O prime B minus O prime A. Okay, O prime B minus O prime A. Okay, and that length will be this length, and that length will be the proper length. We call this proper length as L naught, right? So this is the proper length, O dash, and L naught is the proper length. So how much it is? L naught is, from here to here distance xb prime, this distance xa prime. So length becomes xb prime minus xa prime. Now this is another frame, and xyz, this frame is not moving, it is at rest. This frame is S and it is at rest. Okay, so this frame is at rest. To the observer of the frame S, for this observer, this length, the rod AB is moving with a constant velocity V, and its length as measured by the observer in S, how much it will be? It will be xb minus xa, and for this observer the length will be non-proper, or we call it a moving length. One thing you note down, the process of measuring the length of a moving object requires that distance of its end from the origin, this O, must be measured simultaneously. Okay, it's not that you measure this distance now and then you measure this distance, from here to here after some time. No, you measure simultaneously O to this point, okay, and O to this point. When you simultaneously measure x2 and x1 simultaneously, mean at the same time, and that length will be L, which will not be proper, because the length, it is in the moving frame and you are outside the moving frame, and if you are outside the moving frame, for you the length will be different. And how we'll find that? By using some equations. So this length is not proper. L is x2 minus x1. This is proper because it is measured in the frame S dash. So length contraction derivation using the Lorentz transformation equations. Now we are having the equations for prime and non-prime, like x1 dash and x1, how they are related. Okay, using the formula and substituting the values here. So, if you find difficulty for understanding the Lorentz transformation equation, Please go to my video for Lorentz transformation equations. I am giving the link in the description of my video for Lorentz transformation equations. You will understand the equations after watching that video. Okay. Now just substituting the values here. Now you will have the relation between the moving length and the proper length. Now you know this is the relation. L0 is the proper length, you know, and this factor, it is always in fraction. If this is in fraction, so L will be less than L0. Okay, so if the observer which is outside the frame, when that observer witnessed about what is the length of the rod, for this observer the length will be shorter. Okay, length is contracted, so that's called length contraction, right? But again, keeping one thing in mind, the length contraction is okay only when V is very much greater, V is very large. V is approximately equal to the velocity of light. V is approaching to C, because you're looking at the graph here. So this is L upon L0. Okay, I mean L0 is taken to this side. So L0 is taken to this side. This becomes L upon L0. And here it is taken V upon C. So this is nonlinear scale actually. But one thing you notice, L upon L0, there is no change. I mean L will be equals to L0 if velocity of the moving frame is small. Velocity is, you know, not too much. Then notice up to here, there will be no change. The change appears only when you cross this point. Then, you know, there comes a contraction. Contraction increases. Okay, length is gone, you know, contracting. And if V becomes equals to C, what happens? If V is equals to C, 1 minus 1 equals to 0. And under root of 0 is what? So this is a point for you to think. What will be the result if velocity of the moving frame becomes equal to the velocity of light? Whether the relation will be applicable or not. So please write me in the comment what is your opinion. Thank you.